So we have an assignment due next week. And if you have any questions about it, you should feel free to email me or drop by. We'll have a review session on Monday. All right. Last time we had defined irreducible tensors. Let's say tensors which are irreducible in the sense that all of their components transform into one another in a way that reflects the geometry. And the definition comes from thinking about spherical harmonics. So spherical harmonics are functions of directions in space which under a rotation the 2L plus 1 components of spherical harmonics rotate into one another. And so from that we bootstrap up to abstract what we mean generally by the components of an irreducible tensor by looking at how these objects transform these polynomials, generally thought of as a function of the components in the spherical basis, transform into one another. And they transform into one another according to these rotation matrices, which are unitary matrices. Okay? They are the irreducible, they're matrices that are representations of SU2 with integer values L. Now those representations, those matrices are, for integer L, are just double coverings of the standard rotation matrices in three-dimensional space, the group SO3. So this really has nothing to do with quantum mechanics at this point. This has to do with polynomials. When we want to more generally think about the spin in the problem, well then we need to think about SU2. So from this defining relationship of how the solid harmonics transform, we define an irreducible tensor in the spherical basis to be objects that transform this way, and then irreducible tensor operators to be a collection of operators. In particular, that collection is if it's a rank K irreducible tensor operator, then it has 2K plus 1 different components. And those components transform under a unitary transformation as a rotation in this manner. Okay. And that is the definition. A collection of 2K plus 1 operators that transform this way is said to be the components of an irreducible tensor operator written in the spherical basis with respect to rotations generated by J. Okay. And that we said was equivalent to thinking about an infinitesimal rotation by a tiny angle. That definition of rotation is equivalent to how these components, what is their commutation relations with the generators of rotation, Jx, Jy, and Jz, or equivalently J plus, J minus, and Jz. And those defined relations are given here. So if we have 2k plus 1 components which commute with or have these particular commutation relations with the components of angular momentum, then we say that these are the components of an irreducible tensor operator with respect to J. Okay. So the important result that follows from this definition is the Wigner-Eckhart theorem, which is really the whole point here. And the Wigner-Eckhart theorem tells us that if I look at the components of an irreducible tensor operator with respect to the angular momentum operator J, and I look at its matrix elements with respect to states that are eigenstates of J squared and Jz, then the matrix elements break up in the following way. Alpha here is just, I mean, why we call it alpha, who the heck knows, but it's always been, I guess Wigner called it alpha and everyone followed his lead. This just means any other quantum numbers. This matrix element breaks up into two pieces. One piece which is independent of the indices M, M prime, and Q. In some sense, it has only to do with the magnitude of stuff, the magnitude of the angular momentum, and the magnitude of, in some sense, the rank here. And then everything that has to do with these directions in space is given by the Clebsch-Gordon coefficient. The Clebsch-Gordon coefficient that is related to the addition of angular momentum, where I add angular momentum J, Mj to angular momentum K, Q, and look at the probability amplitude to have total angular momentum J prime and projection. So, as we discussed, one way to sort of think about this was that if I looked at, sort of loosely speaking, if I looked at something like this, I could think about it as having the same properties of rotation of the product state of two angular momenta. One angular momentum associated with the state, and an angular momentum associated with this component of the tensor.
And when do you write out both cats and when do you plug them in?
So, we'll talk about it in a moment how we actually use this to do calculations. Remember, we looked at the example at the end of class last time, where we looked at the example where this was a, we looked at the example where we had and when we looked at this in the position, this was the qth component of the electric dipole operator. And when we looked at this in the position representation, what we ended up with was where when we wrote out this matrix element in terms of wave functions, dq here was the charge of the electron times the qth component of position in the spherical basis, which is, you know, some constant times r y1q. That was really the whole point, that the angular dependence of this component of the vector, which is the rank 1 tensor, was the same angular dependence as the spherical harmonic of rank 1 projection q. So when I'm writing this loosely, what I'm saying is that this is like my ket 1q, this is like my ket ln. And when we have the product of two angular momenta, that product can be written according to the Clebsch-Gordon expansion as Clebsch-Gordon coefficients times sum total, where J prime here goes between K minus J and K plus J, and then N prime goes from J minus J prime to plus J prime. So the point I'm trying to make here is that the way to interpret the Wigner-Eckhart theorem is like starting with some angular momentum, adding in some angular momentum, and then ask what is the probability amplitude for finding that angular momentum. And that probability amplitude is nothing more than the Clebsch-Gordon coefficient. What's left over is everything that has to do with the radial components, the things that don't have to do with the directions in space, but just the distance from the origin.
So to get the reduced element, you just brute force it?
You just brute force it. So, so let me say a few things about this, you know, so how do you use the Wigner-Eckhart theorem? What's the point of it? Firstly, I want to just first thing I want to talk about is conventions. Just like the Clebsch-Gordon coefficients, if you look in a textbook, there's like a jillion different conventions about how people define the Clebsch-Gordon coefficients. The same thing is true about the Wigner-Eckhart theorem. The convention I'm using here is the so-called Condon and Shortley convention. What do I mean by that? Condon and Shortley were sort of pioneers in working out all of the physics about atomic molecular spectroscopy back in the, oh gosh, who the heck that was when that was, the 40s. Under this convention, this thing which is called the reduced matrix element is not at all a matrix element. If it were a matrix element, then if I took the conjugate, I would expect to be able to, you know, switch the bra and the cat. But this is not true in this convention. Okay? This is not a matrix element. That's why it's got that double bar on it. It's just the piece that's left over that's not the Clebsch-Gordon coefficient. How can we see that in this convention this is not true? I mean, look, if I look at, let's look at the other way around. Let's say I looked at this matrix element. Okay, well this, according to the Wigner-Eckhart theorem, is this reduced matrix element times this Clebsch-Gordan coefficient. Right? However, the complex conjugate of this does not equal this. Right? There's some rules with -1 to the jk plus 1 and the square roots of 2j whatever when you want to trade these two things. They're not just one is not just the complex conjugate of the other. Which it would have to be if this star was equal to the thing with the j prime, when the j switched. So often you will see this defined, in order to make this thing have the right properties, you will sometimes see, and often like in Saccharide, a factor of square root of j plus 1 there. Under that case, then the reduced matrix element would have this property. But I find it a total waste and a confusion to do that, because you never actually need, it's to count, what does this mean at the end of the day? Well, you would calculate this, you calculate the Clebsch-Gordan coefficient, then you multiply by that, and then you get the reduced matrix element. It's an extra factor to worry about that you don't almost ever need. So I don't like that convention, but it's a convention that you'll see. Another convention is, instead of using the Clebsch-Gordan coefficient, to use the 3j symbol, the bigger 3j symbol, which is the same thing as this, except it has different minus signs in front of it. It's just a warning. These are things, unfortunately, there's different standards, there's different conventions, and there's not uniform agreement amongst all of those things. So, the other point related to the question that Aaron asked is, how do you calculate the reduced matrix element then? Well, the answer is, we'll get rid of this thing, go back to convention that I prefer. What we see here is the reduced matrix element is the ratio of the full matrix element to the Clebsch-Gordan coefficient.
Is this by purpose that you've got one double bar and one single bar?
No, it's not on purpose. It's a mistake. So, what this means is that I can calculate this once for some convenient choice of m prime, m, and q. I actually have to calculate the full matrix element for some particular choice. And I do that for some choice that's as easy as possible. Divide by the Clebsch-Gordan coefficient associated with that particular choice of m, m prime, and q. And then you have it. And then the matrix element for all other possible values of m, m prime, and q are just tack on the Clebsch-Gordan coefficient. So one of I would say most often we don't care about the actual value of reduced matrix element. It is what it is. What's important, as we'll see, is the ratio of these matrix elements for different values of m, m prime, and q. Because they tell us something about the branching ratios associated with different transitions that are associated with the absorption and emission of electromagnetic radiation. And all of that is just the Clebsch-Gordan coefficient. We'll see that in a moment. Now, that's not, there's one case where, so rarely do we actually use the Wigner-Eckhart theorem as a way of simplifying calculating a matrix element. Because at the end of the day, I have to calculate at least one of these guys. I mean, it's a simplification of a little bit because maybe there, it depends how many Q's are possible. And then I just have, I've reduced it by some factor. But it's not really generally about that. It's about the ratio of the different transitions. Except in one case. There's one case where the Wigner-Eckhart theorem gives us a giant simplification. And that's the Landé projection theorem, which is what you have in homework, but let me just say a few words about that. So look, the Landé projection theorem is a special case of the Wigner-Eckhart theorem. And the Landé projection theorem says the following. Suppose that alpha equals alpha prime and j equals j prime. So I'm looking at the matrix element of some tensor operator restricted to the 2j plus 1 subspace. So I'm looking at matrix elements in 2j plus 1 dimensional subspace. Of mj values. Okay? For example, suppose I have the Zeeman interaction. Which is the interaction of a magnetic dipole moment with some static magnetic field. Okay? Now, this is equal to mu b L plus 2 mu b S dot B minus the nuclear magneton times the G factor times I dot B. Okay? So, for example, let's suppose the strength of the Zeeman interaction is small compared to the hyperfine splitting. Then the perturbation doesn't mix strongly states that are associated with different values of F, but instead strongly mixes the different M sub F values within a given F, right? So, example, let's say we have sodium 23 has a spin 3/2, has an F equals 2 and an F equals 1 manifold. Remember that? Now we put on this magnetic field in this problem. Well, we need to then diagonalize due to degenerate perturbation theory, and we need to diagonalize this Hamiltonian in either of these subspaces, right, in order to get the perturbation. Of course, to higher order, we would then have, second order perturbations, which would have to do with the energy difference between the hyperfine manifolds and the strength of the Zeeman. That would give us what we call quadratic Zeeman shift. But let's just say that that's a tiny effect, because this is small. Okay? Well, we have to then calculate matrix elements of these operators. We need to calculate the matrix element of mu with respect to, so this is the 3s 1/2 manifold, right? So we have 3s 1/2 f m sub f prime of the interaction and we're saying this is small, so we restrict to a particular f, and we need these matrix elements. Right? So, we have here an example of the application of the Wigner-Eckhart theorem, in the sense that we have a vector here. I can write this in the spherical basis. So I need these guys. Let me leave it as a vector, but I just wanted to say that's an example of a particular component, that at the moment we need this vector. Well, what the Landé projection theorem says is the following. Well, before I do that, I guess I should mention the following question. Is mu a vector with respect to the angular momentum operator F? Yes. How do we know? Is mu a vector operator with respect to F? Well, first question, is it a vector with respect to the orbital angular momentum operator L? We have to be quite careful about that. Because if I look at, say, this was along the z direction, then I would have SZ. Yeah, that would work. So all the individuals work, but in addition, if I look at FZ, or the components of Fi commuting with some component Uj, what I need this to be true is this is equal to epsilon ijk Uk. That's one way of looking at it. And that's certainly true, because each one of these guys has the right commutation relation with the appropriate L, S, or I. And therefore, mu is a vector with respect to the total angular momentum operator F. So that's fine. So then we can think about the Wigner-Eckhart theorem. Oh, yeah, of course, the other thing that would be true, have to be true, is that F squared has to commute with each component. Note that L squared wouldn't do that, right? Because L squared, I'm sorry, J squared wouldn't do that, because J squared does not never mind. That's not correct what I'm saying. But F is definitely a vector. Okay, but let me get to the main point then. The Landé projection theorem. What the Landé projection theorem says is if I have a tensor operator, particularly if I have a vector operator, and it is restricted to this subspace, then the following is true. This is the Landé projection theorem. It's something you're proving for homework, but it has an important geometrical meaning and then a very practical import for how we use this for calculations. It's a special case of the Wigner-Eckhart theorem when we have the only thing that changes is the end value. Okay, what does it say? Well, it's saying that basically, loosely speaking, in this subspace, the operator mu has the same matrix elements as mu dot f divided by the magnitude of f squared divided into f times f over the magnitude of f squared. Let's think about what this means geometrically. Geometrically, what is this? Well, I can think about this as a unit vector along the direction f. So here's as a classical vector f. Here's the unit vector f divided by the magnitude square root of f squared. Here's the vector mu. Here is the projection, let me call this thing e sub f. Of mu onto f. This operator is saying the vector mu, the only thing that's very important are its components along the direction f. All the other matrix elements, all the parts that have to do with its components transverse that don't contribute. So, what's going on physically? Let's think about a simple example where I have no orbital angular momentum, I just have spin. Okay? And let's say I ignore the nuclear magnetron, which is tiny compared to the Bohr magnetron. And I put on a very strong magnetic field. Well, I don't really mean to say it's strong. What I mean to say is it's weak compared to the hyperfine splitting, so maybe I'll make it small. So I put on a magnetic field. We know in the absence of the magnetic field, these two guys are coupled together into F. And I can loosely think about this as there's a well-defined projection along F, there's a well-defined magnitude of F, but there is an uncertain projection of the individual electron and nuclear spins. That's the coupled representation. The magnitude is defined, the projection of the magnitude is defined, but the projection of the individuals aren't. Now I have this magnetic field which wants to move the electron separate from the nucleus, but it's weak. That was our case that the Zeeman shift was small compared to the splitting. Under that case, what it's saying is that the only thing that matters is the projection of this S vector onto F because they rotate together. This thing rotates around so fast that it keeps a constant projection below F. The Landé projection theorem is not an approximation, it's an exact theorem. The approximation we made was to say that we had low order perturbation because our magnetic shifts were small compared to the splitting. But the Landé projection theorem is exact. And its import then is the following. This makes things easy to calculate. Why? Well, these guys are the matrix elements of that momentum. We know what they are. If this was along the z direction, this would be m sub f, right? Because this is an eigenstate, and if it was x, it would raise or lower. What about this part? Well, notice that this is a scalar. respect to rotations generated by F, which means that this is irrelevant. It doesn't matter what F it is. All that's left over here is some constant that depends on F and alpha. So what you will see in your homework is this is, for example, how you calculate what's known as the G factor associated with the splitting of the magnetic sublevels in a magnetic field. There is a what's called the Landé G factor. That is to say, in this subspace, mu dot B is approximately G sub F at B. Whereas really what we had was G sub spin plus G sub I times spin. When restricted to that subspace, this whole thing looks like the angular momentum operator F. So the Landé projection theorem is often used, and the Landé projection theorem allows us to more simply calculate these matrix elements as opposed to what you did for homework. According to that nasty homework assignment. Remember that nasty homework assignment? You had to decouple all of the F's into the J's and the I's, write out all the Clebsch-Gordon coefficients, and then take it. That was a total pain in the butt. You never ever do that. What you do is you just write down the G factor. Maybe you don't even calculate the G factor, you'll look it up. And once you know the G factor, well then it's just matrix elements of F. Okay, so other than the Landé projection theorem, rarely do we actually use the Wigner-Eckhart theorem to fully calculate the matrix elements. Instead, what the Wigner-Eckhart theorem really is about selection rules and branching ratios. And for that, I now want to turn our attention to thinking about the problem of absorption and emission. Of electromagnetic radiation. So this is where we were a week ago. We had written down the interaction Hamiltonian. We had made the gauge transformation and expanded it as a multipole expansion. So we had, for example, the interaction Hamiltonian we had was so our interaction Hamiltonian was in our multipole expansion was the interaction of the dipole moment of our atom with the electric field of our electromagnetic radiation at the position, center of mass position of the atom. That's what this is. And then we have an interaction of the magnetic dipole moment of the atom with the magnetic field, the quadrupole moment of the atom with something that has to do with the local gradients of the electric field at the position of the atom, etc. Okay? And so what we know, let's suppose I have, for example, a plane wave. So let's say that this is equal to the real part of a plane wave. Okay? That's our electromagnetic wave, our radiation. This is the polarization. Let's say it's a polarized wave. This is the amplitude. This is the wave vector, this is the frequency. All right, so this is V0 over 2. Plus the complex conjugate. This, as you recall from your studies previously, is a problem of time-dependent perturbation. And we have the issue of resonance. If I drive my system with oscillating forces, then I dominantly drive transitions whose energy difference is near the resonance associated with that frequency. And what the Fermi's golden rule tells us, and we'll come back to what this really means in a few weeks, tells us that, for example, the rate of absorption is equal to 2 pi over h bar the square of the positive frequency component of the matrix element of the interaction times the delta function when E final minus E initial is equal to h bar. Okay, this is Fermi's golden rule. Fermi's golden, what do I mean by H plus? Well, here I have two pieces. If I have a wave, I have a part that is associated with this, and the conjugate, this part is what's called, gives rise to the positive frequency component. And this is the negative frequency component. This part would have to do with emission. This part has to do with absorption. In this particular case, for example, for the dipole term, this would be equal to 2 pi over h bar, the matrix element of dv dot epsilon psi initial E0 squared over 4 times the delta function. Okay? This would be for the dipole term. There was another term here which would have to do with the matrix element of the magnetic dipole moment, and another term that has to do with the matrix element of components of the quadrupole tensor. So, now, as a little aside, of course, this delta function only has meaning when we have some distribution either of energy levels because of a density of states. If we have some density of levels, if there are many different levels. For example, if we have spontaneous emission, we know that the excited state is not an infinitely sharp line, but there is a distribution with a line width associated with it, so we would integrate over the atomic line width. Or we might have a spectral energy density of electromagnetic waves, like if we're talking about a lamp or starlight or something like that, where we had spectral energy density, we would integrate over omega. And we would end up with the Einstein B coefficient, for example. So, what can we see here? Well, the transition rate, the absorption rate, depends on these matrix elements. It depends on the matrix elements associated with these moments of the charge distribution. The dipole moment, the electric dipole moment, the magnetic dipole moment, quadrupole moment, etc. So, firstly, the first thing to remember is how big are these different terms relative to one another? So let's talk about the dominant effects in atomic absorption. Well, question is, how big are the terms? And that's one question, is how big are the matrix elements? Let's talk firstly about the electric dipole. Well, the interaction strength here depends on this square of this guy. The first question is, what's the characteristic size here in the atom? Well, we know that if we're talking about atomic physics here, and we're talking about the characteristic size of the dipole, we have those characteristic sizes. It's on the order, I mean, there'll be some perhaps constant out front, but it's of this order. So the transition strength depends on the intensity of the field and the characteristic dipole strength. What about the magnetic dipole? Well, now we're talking about the same kind of thing. But now with the magnetic dipole moment and the strength of the magnetic field. Well, firstly, how big is this? Well, in the atom, what we said from the characteristic units, this was the Bohr magneton, right? This was E h bar over mc, which we said was which is equal to, actually, the fine structure constant times the same electric dipole term. Remember, this is the speed of the electron in units of the speed of light. So it's smaller by that amount. In CGS units, the magnitude of B is equal to the magnitude of E for a plane wave. So if I have a plane wave, my expectation is that the magnetic dipole part of this interaction is negligible compared to the electric dipole part, because the ratio of this rate to this is the fine structure constant squared. This is a much smaller interaction strength. It's 137 fractional times smaller, squared than this. So unless this dipole matrix element vanishes for some reason, the magnetic dipole interaction is a negligible contribution to the electric compared to the electric dipole. So this is the dominant effect. What about the quadrupole? Well, let's think about the elements of the quadrupole moment. What are they? Well, they depend on the squares of the distance of the charges from the origin. So the order of this we would expect to be something like that, right? So the interaction strength here, which depends on the matrix elements of this guy, to this. Well, what about this derivative? This is the gradient of the electric field. And my electric field, we said, if we're thinking about this as a plane wave, then the gradient here is the derivative, which is basically the wavelength. That's the scale over which the electric field is changing in a plane wave or an electromagnetic wave. So this is going to be on the order of the strength of the dipole moment, the quadrupole moment will be an order of that. We have K all right? So how does this compare to this? Well, what are we talking about with K here? K is the wave number. K is omega over C. What omega are we talking about? Well, we're talking about an omega near an atomic resonance for this thing to make sense. So what omega are we talking about? We're talking about an omega, which is the energy, which is the Hartree, over h bar. That's our frequency. That's our characteristic frequency, which we recognize as the fine structure constant times E squared. I'm sorry, times 1 over 4 radius. It's 1 over length. So, putting that all together, what we see here, plugging that in, we have 1 over A naught, we have the fine structure constant. A naught cancels. We see that, in fact, the electric quadrupole moment in a plane wave same order. The magnetic dipole was alpha times smaller than the electric dipole moment. So is the electric quadrupole moment in this plane wave. So if I have a plane wave and I'm shining it on my atoms, or something that approaches, I have a laser beam, I'm shining on my atoms, I have starlight, it's being absorbed by atoms in astrophysical space. The strong interaction is the interaction with the electric dipole. Then, to next order, we have corrections, which are corrections due to both magnetic dipole and electric quadrupole, which are of the same order, in fact. Now, it may be the case that this vanishes for whatever, for all components. In which case, doesn't mean that the interaction is forbidden or completely forbidden, it's just not strong. And in order to generate the same rate of absorption, I need to crank up the laser intensity, 10,000 times more in order to get the same rate of absorption. Because this matrix element is reduced by a factor of 1 over 137 or so. Okay. So that is why when one talks about transitions of absorption and emission in atoms, one talk about allowed transitions, which are the electric dipole allowed transitions. There's a language that's used that's a little bit confusing. It's not that the transitions that are not electric dipole possible, they're impossible, they're just not strong. They're allowed, they're just not strong. There could be completely forbidden transitions that no matter how strong the field are, the selection rules forbid them. But the language that one sees often is the allowed transitions are the electric dipole allowed transitions. I should say there's a little other jargon here. One talks about these transitions as electric dipole is electric 1, electric quadrupole is E2. Magnetic dipole is M1. So one has this jargon here. One talks about this is an E1 allowed, this is an E2 allowed, this is an M1 allowed. Okay. However, the Wigner-Eckhart theorem defines selection rules. What do I mean? Let's consider one electron in valence shell. So let's think about hydrogen, or the alkalis, or singly ionized calcium. Okay, one electron, just to start. So that one electron then is the optically active electron, and we think about its orbital, or its state, as the state that it can be excited. Okay? That in our excited state. So what we're considering, let's consider first electric dipole transition. So the interaction, the rate of absorption is proportional to the rate of transition actually. Between two states, which in general might have hyperfine structure in them. Okay? So, and the particular component here depended on the polarization of the light. Remember, we had V dot E, and the polarization vector, I mean, really this was the component along that polarization vector. What can we say about this? Well, from the Wigner-Eckhart theorem, this is equal to the square of the reduced matrix element times the Clebsch-Gordon coefficient. In fact, the rate of absorption depends on the square of that Clebsch-Gordon coefficient. So, from this, we learn the following. There are selection rules. If I'm going to absorb and go from one state to another, there are some restrictions based on, firstly, on the symmetries and conservation laws. The selection rule for E1. What can we say here? Well, we see, according to this, M prime has to equal M sub f plus q. That is the only way that this Clebsch-Gordon coefficient is possibly non-zero. If the magnetic sublevels don't add up, then I don't conserve angular momentum along the z-axis. And since Q, in this case, can take on possible values, this is a rank 1 tensor, Q can take on values +1, -1, or 0. So that means delta M can be 0, +1, or -1, depending on Q. Moreover, we know that F prime here can be equal to either the magnitude of F minus 1, F, or F plus 1, because of the addition of angular momentum. So that tells me that delta F can be 0, +1, or -1. Note, generally F equals 0 to F equals 0 is completely forbidden. Because there's no way, if F were 0, I can't add 1 unit of angular momentum and get back 0. That's just impossible. Now that's kind of, in this case, it doesn't really matter because F will never be 0 in a 1 electron atom. I have 1 electron. I can't get. Oh, well, that's not true. That's not true because I can have a nuclear state. Never mind. That's still it's important. What else can we say? Well, we have another, beyond the Wigner-Eckhart theorem, we have parity. parity tells us that delta L must be odd. However, there's more than that, because what did I say here? So note, I didn't make this point here. What is D? D is the charge of the electron times the relative position of the electron to the nucleus. D is a vector with respect to L. It is a vector with respect to J, and it is a vector with respect to F. That's why I was able to use the Wigner-Eckhart theorem with respect to F as a good quantum number. But it's also a good quantum number with respect to J, which means that if I were to write my state J, L, F, M sub F in the, there's also an I in here, I can write it down in an S, because those are fixed, in terms of the uncoupled basis, since the dipole operator doesn't act on the nucleus, it only acts on the electron, we will have in this matrix element only matrix elements. We will have matrix elements within a given J. And if J is a good quantum number, we will have, in addition to that, we'll have a variety of matrix elements of the form like this, if we were to decouple and write them out. Now, M sub J is not a good quantum number in this case, but J is. And this matrix element will be of the form, according to the Wigner-Eckhart theorem, so the other thing we see in here, every term in this matrix element also has a restriction on the possible values of change of J and J prime. Because this is a vector with respect to J, I also have the rule that delta J can change by +1 or -1 or stay the same, but no J equals 0 to J prime equals 0. If Mj were a good quantum number, then that would be the same rule here, but we're looking at M sub F. Moreover, I can uncouple again. I can uncouple the orbit from the spin. And D only acts on the orbit, not on the spin. And thus, we have yet another rule here, which is delta L could be 0 ± 1. However, parity says it's odd. So delta L equals 0 is impossible for a U1 transition. So, based on parity and rotation symmetry, we have selection rules for electric dipole transition. For example, let's look at sodium again. had the 3s1/2 ground state, which had hyperfine structure. These are my m sub f values. Similar structure for rubidium 87. Then we have some excited states up here. We have the 3p1/2, which has the same hyperfine structure, although less split. Oh God. Let me draw this differently. Let me try to keep the house. This has. Hard to see in this perspective from the chart. Okay, so I've drawn out here in quite a bit of detail the energy level structure associated with the D1 and the D2 line of sodium, or rubidium 87, has the same kind of structure. Okay, first question. These are my F levels, right? Because nuclear spin here for this guy, the nuclear spin is 3/2 for sodium. So, question. If I start here, which levels can I go to? Firstly, can I make transitions between here and these levels? Yes, delta L is 1. This is L equals 0. This is L equals 1. So parity and angular momentum are fine. J can change by 0 or 1, but no 0 to 0. Can I go from here to here? What is J here? This is a half. J is a half. And what's J? A half. Is that okay? Yes, that's fine. J can stay the same. And J can change by 1. So all of then I have to think about within the F's. So if I'm here, I can go F equals here. This is F equals 2. I can go from 1 to 1, and that's fine. So for example, if I start here, I can go to this level. I can go to that 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 level. And if I go here, where can I go up here? Can I go from here to here? Yeah, I can do that. Because that is delta F equals 1. And delta N equals minus 1. And I can go to here, and I can go to there, and I can go to there, and I can go to there, etc. But I can't go up here, because that's delta F equals 2, etc., etc., etc. If I start here, for example, here I can only decay down to here, but I can't decay to here. Notice, if I start here, there's only one possible transition here. because 3 can't go to, it can go to 2, but delta m can only change, it should have been plus, excuse me, can only change by 1.
And why isn't the same state at 3p1/2 possible?
Sorry?
At 3p1/2, you've got f equals 2 and
Yes.
f equals plus 2. That's
I can certainly absorb, indeed I agree. What I meant is from this state,
Yeah.
there's only one it connects to in the ground
And
method.
why isn't it possible to the f equals 2 and f equals plus 2 in 3p1/2?
Oh, good question. Why can't it decay from here to here?
Yeah.
Because delta L is 0.
Okay.
I have to change L by 1. Now, I can do that by a magnetic dipole transition, we'll get to that next week. But in electric dipole, impossible. In fact, it's extremely tiny from spontaneous decay because of the frequency dip, but we'll get to that separate. But if I were to, in terms of the electric dipole allowed transitions, this is the only one. Therefore, this is what's known as a cycling transition. Because if I put on a laser beam that was resonant here, it can only decay back to here. That's very important. If I want to scatter lots of photons off of an atom, I should do it on a cycling transition, because otherwise it gets stuck in some other level. Yeah.
So, what did you say was the process that we can sometimes with low probability end up in f equals 1? Because we need a repump laser.
No, I can't do that. That only has to do with the, if I didn't have purely, if I don't have purely this polarization, and I have a little bit of that, then I can decay. But if I have exactly that point, there's just no way I can do that. Okay. The other point that I want to emphasize, and we'll talk about next time, is which of these transitions is driven, if I'm talking about absorption, not emission, spontaneous emission, but absorption, depends on the polarization of the light. And in particular, what we had was the matrix element between the initial state and the final state of that operator, right? So whether I'm talking about this, whether Q is 0, +1, or -1, depends on the polarization of light. Relative to what I'm calling the z-axis, remember d0 is dz, d +1 is dx plus I dy over root 2. D -1 is this, the minus sign. So depending upon whether my electric field is polarized along z, x, or y, determines which of these transitions I drive. Note, important note, nowhere do I say what the direction of k is. Nowhere do I say what direction this wave is propagating in. That is irrelevant. Of course, if k is along the z direction, there is no component z. But the atom doesn't care what direction the light is propagating is. The atom is just sitting there and it's going up and down and around, and it doesn't know. I mean, yes, there's a radiation pressure, and we'll talk about the center of mass, but as far as the electron relative to the nucleus, it's a local thing. It's right there at the electron. So what I call z, x, or y is independent. I call it the k direction, but I don't have to. And this is often a confusion about whether I'm talking about circular, does this circular polarization or linear polarization? It's not that. It's circular or linear with respect to the axis I'm calling z, not the axis I'm calling k. They may be one and the same, but they don't have to be. And it's a constant confusion. We'll get back to that next time. All right.